Love the music. Next time I want pyrotechnics. Building a large, reliable quantum computer is one of the biggest technological advances ever attempted. It's a real moonshot. I think that's the right phrase. When I founded Riverlane 7 years ago, many people in the industry, in the field, thought that this would never be possible. But I knew they were wrong. I think what Moore's law teaches us is that the compounding effect of improvements and innovation year on year makes today's technology look like magic. I'm going to talk about how we get from the quantum computers we have today to large, reliable quantum computing. I see there are two main challenges. So the first is to increase scale. We need to go from hundreds of qubits to hundreds of thousands and millions of qubits. And the second is to improve the reliability of these systems. So we need to improve the error rates of the components, and we need to add quantum error correction. And that's what we're doing at Riverlane, and I'm delighted to tell you more about it. So first, let me start by motivating why I'm interested in quantum computing. In many industries, computers are used to design new products. In the aerospace industry, simulation of the physics of flight is used to design the next generation aircraft. But if we try to simulate the interaction of an organic molecule with a protein in healthcare, or the way that electricity moves across a battery, if we try to simulate how a catalyst enables a reaction in an industrial process, we hit this wall. And the problem is that the underlying equations of motion are quantum mechanical. And so building a quantum computer enables us to solve these problems. I really like this table from colleagues at Zapata and Intel. So they're looking at here the potential application of quantum computing to achieve net zero. And across the top are many different application areas. So the search for better batteries or CO2 capture. And then each row shows you the kind of underlying properties of the systems that we would like to be able to simulate, we would like to be able to solve. So I'm just going to pick one example here, the production of synthetic fuels. And we'd like to understand the electronic band structure in this problem in order to develop a better catalyst. So the way that synergas, so the creation of hydrogen, is produced is typically using steam methane reformation. Right? So this takes methane in and outputs hydrogen and carbon oxides. So the catalyst that enables this reaction is very common, is a very common kind of process. Typically, nickel oxide is used in this process, and this is a sort of typical catalytic problem. In fact, it is used in about 25% of the world's industrial energy use is in these types of reactions. So what would it take to use a quantum computer to simulate this system? So on a classical computer, the calculation of the electronic band structure of nickel oxide is essentially impossible, at least to accurately represent this. We can make approximations, but to do this exactly would not be possible with any classical computer. So if you take the best quantum algorithms known today on a quantum computer, we require 10 billion quantum operations and around 5 million qubits. But the remarkable thing is that this takes 8 days. Right? This is a computation that is now possible with a quantum computer. So the problem is that we need to get from today's quantum computers, so they can do 100 operations, 100 qubits, right? And this is amazing. They look something like this. There's a dilution refrigerator, and the qubits are at the bottom. But where we need to get is here, right? We need to get to billions of operations. And there's a massive gap between where we are today and useful quantum computing. And so that's solved by a technique called quantum error correction. So with quantum error correction, we take many physical qubits and we add redundancy, so that if any one qubit fails, we can still correct, so the system can still recover. So we turn physical qubits into logical qubits to create stability with noisy components. In much the same way that a solid-state hard disk works. So solid SSD cards are built out of noisy components, and there's active error correction on top. Right? So this is a good analogy, I think. So what do we need to do to implement quantum error correction? This is a diagram of the process of correcting errors. So at the bottom are the qubits, and we measure the syndromes. This tells us some indication of which errors occurred. The syndrome data is passed to a decoder, whose job is to infer the most likely error given the syndrome data. Having solved the decoding problem, we need to make a correction and apply that to the qubits. And the challenge is to do this at a rate of megahertz. So we need to do this 1 million times per second because the syndromes are generated in a superconducting system at that rate. So what happens if we can't solve this in a millisecond? There's an exponential slowdown of the quantum computation. So let me explain that. So assume the error correction cycle takes 1 microsecond. Right? The quantum computation requires 10 to the 10 gates, and it takes 8 days. Great. Now, if it takes just 1% longer, 1.01 microseconds, then the computation takes 1.01 to the power 10 to the power 10, which is longer than the age of the universe. So this is a catastrophic failure of the system. In fact, I consider this to be the 6th DiVincenzo criteria. So in 2000, David DiVincenzo set out 5 criteria to build a large and reliable quantum computer. He said we need 5 things. We need a scalable physical system with well-characterized qubits. We need the ability to initialize those qubits. We need long coherence times, much longer than the gate operation time. And we need a universal set of quantum gates. And finally, we need measurement. In 2000, the question was, could you build a qubit at all? And so classical computation was considered to be free. But without being able to decode fast enough, we won't be able to build a scalable quantum computer. So the 6th criteria is sufficiently fast decoding. So I'm pleased to say that we can now decode and correct the signals at microsecond rates. So these are the latest performance figures from the Riverlane team, developed on an FPGA decoder. They show the performance of our decoder at various different noise rates. So the left-hand axis is the decoding time, and the right-hand axis is the number of physical qubits. So as you increase the number of physical qubits, the problem of decoding gets harder. So this data is on the surface code, so is applicable to 2D planar architectures, think superconducting qubits here. And this is a result of many years of improvements at the various levels of development. So better algorithms for decoding, better implementations of these algorithms, and a collaboration between experts in quantum error correction and experts in chip design. So we've also developed the world's first ASIC, and on the left-hand side you can see the floor plan of this ASIC. The chip came back a couple of weeks ago and is now well characterized, and I can say that we can now decode at a rate of megahertz and make those corrections in the control stack. So we can take signals from the syndrome data, pass them to the decoder, and have that decoder make corrections and apply them in the system in the real-time loop at megahertz. So the chip that came back from the fab looks like this. We collaborated with Skywater and eFabless to do this. Super exciting development for Riverlane. It's the world's first ASIC decoder. So we work with quantum groups, so hardware companies, and academic research groups that are developing the qubits. Right? There's no good building a very fast decoder if it doesn't correct for the real errors that are occurring in the system. And this is another really important side of the problem. I think often people think about quantum error correction in terms of switching something on at the end. Like, we're going to develop these quantum computers, and then in 5 or 6 years' time, suddenly try to do fault-tolerant quantum computing. That's not the case at all. The way to build large and complex systems is to make increasingly large system-level tests. The first system-level tests are randomized benchmarking. They're characterization of 1, 2-qubit error rates. The second system-level tests are randomized benchmarking in the presence of other operations. The next test is a stability experiment. This you can do on something on the order of 9 qubits. It tells you if your stabilizers in your code remain constant. After that, you can perform quantum memory experiments, first showing that the system is stable, and then ultimately showing that logical errors are lower than physical errors. And this roadmap continues. Right? There are a sequence of increasingly complex experiments which teach us about system-level integration and how errors occur in the system, how errors occur in quantum systems, so that we can learn to correct these errors in the decoder. So we're very grateful to work with many of the leading experimental groups on this. We've learned a huge amount about errors in quantum systems, but there's a lot more still to learn. And so today I would be very keen to talk to anybody developing quantum systems, research groups here in Japan to collaborate on this. I think that no one company or even one country can build a large, reliable quantum computer. The way to do this is to collaborate. I'm convinced that this will not happen overnight. Like, this will take many years, and we will get there as a result of many ideas, many compounded innovations and ideas that combine. I'm sure that in 5, 6, 7 years, the effect of that will be that the technology available by the end of the decade will look like magic. Thank you.
So we have a little bit of time to take some questions. So if anybody has any questions, please raise your hand. 少し時間がありますので、何かご質問がある方はどうぞ手を挙げていただければと思います。どなたかいらっしゃいますでしょうか。Does anyone have any questions? Yes, gentleman in the back.
Thanks very much, Steve. Fascinating. A lot of it is a bit beyond me, and there's one calculation there that was a bit beyond me. Maybe I've missed something, but you had just showing a slowdown in the decoding from 1 microsecond to 1.01 microsecond. So that's not a dimensionless quantity. So why can you just raise it to 10 to the power 10 to the power 10? Maybe there's something really obvious that I should have understood.
No, it's not obvious. So Barbara Terhal realized this in 2015. It's called the backlog problem. So what happens is that new syndrome data is arriving all the time, And when you want to perform the next logical operation, you start the clock. Now you have to decode everything in the past. New data is being generated as you're solving your decoding problem from the last batch. And when you're done, you can then apply the next logical operation. Right, so the problem is that if you're a bit too slow, then your next problem to solve is now even longer. And so this builds up and up and up, and you get this exponential backlog problem. Yeah.
Thank you. Thank you very much.
Right.